Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some interesting work in image generation. We'll be looking at a paper titled DMM Building a Versatile Image Generation Model via Distillation-Based Model Merging. So the researchers point out that we have tons of specialized text-to-image models now, fine-tuned for specific styles or subjects, but this creates problems like, needing huge amounts of storage and having lots of redundant parameters. Trying to just average these models together doesn't really work well because the styles can clash. This paper introduces DMM, which stands for Distillation-Based Model Merging. It's a new way to combine multiple specialized models into a single versatile one that can generate images in various styles based on style prompts. It uses a technique called score distillation to achieve this compression. And you can really see this versatility in action in Figure 1. It shows a bunch of images generated by this single DMM model. You can see it covers a really wide range, like realistic portraits, different kinds of anime styles, landscapes, even things like a rabbit or an apple. This just highlights how the one DMM model, guided by those style prompts we mentioned, can capture the essence of all those different specialized models it was trained on. Pretty neat. Building on that idea of combining multiple models, Figure 2 shows us how they actually train this DMM model. It illustrates their distributed training framework. You can see in part how they use a GPU cluster. Each specialized teacher model, representing a different style, gets assigned to its own GPU node, and they jointly supervise the single student model, which shares its parameters across all these GPUs. Those style prompts we mentioned earlier are shown here too, as learnable embeddings in a codebook, helping differentiate the styles. Then, part shows something pretty useful, how they handle continual learning. This means they can add new teacher models, new styles, later on without retraining everything from scratch. They basically add a new embedding for the new style and use the already trained frozen model to help guide the student, preventing it from forgetting the styles it already learned. So Figure 3 gives us a closer look at the actual distillation process itself. How the student model learns from a teacher. We see the teacher UNet in pink and the student UNet in blue, both getting the same noisy input image. The style prompt we talked about earlier is fed into the student model here too. What's really shown clearly in this figure are the specific ways they train the student. There's the score distillation loss, which basically makes the student's noise prediction match the teacher's. But there are two other key losses shown here. Feature imitation, where the student tries to copy the internal features of the teacher model, and a multi-class adversarial loss, which uses a discriminator to make sure the student's generated images look like they belong to the correct style distribution. These three losses work together to train that versatile student model. Okay, so we just saw how the DMM model learns from the teachers using those different losses. Figure 5 now gives us a really clear visual comparison, showing how well that learning actually worked. For each prompt, like portrait photo of a girl or handsome boy, you see two rows of images. The top row is generated by the single DMM model using the appropriate style prompt, and the bottom row shows results from the original specialized teacher model for that style. You can see, the DMM model's outputs look remarkably similar to the teachers across these different styles, from realistic photos to anime to even food. It really shows the distillation successfully captured the essence of each teacher. So, Figure 5 really drove home how closely DMM can replicate the original teacher styles. Going further, Figure 6 gives us another look at this versatility. For the prompt about an elf girl, you can see DMM generates images in a bunch of different styles, from more realistic to various anime looks, all looking pretty consistent within their style. And then, Figure 7 shows something practical. Results from an accelerated version called DMM-SPLAM. The key thing here is that these images were generated in just 4 inference steps, which is, really fast for diffusion models. It shows that this DMM approach can also be efficient. So we've seen the kind of versatile results DMM can produce, even quickly. Table 1 now gives us some quantitative backup, showing how much each part of their training method actually helps. This table uses a metric called FIDT, where a lower score means the DMM model's output is closer to the original teacher model's style. You can see they start with just score distillation, getting an FIDT of about 80.7. Then, adding the feature imitation loss we talked about earlier brings it down to 79.3. Adding the multi-class adversarial loss helps a bit more, down to 78.4. And that final synthesized fine-tune step brings the score down to 77.5. This is really close to the teacher reference score of about 75, which is like the best possible score they could hope for. So it really shows that each of these pieces, the feature imitation, the adversarial loss, and the fine-tuning, they all measurably improve how well DMM captures the original styles. Okay, so Table 1 gave us the numbers, specifically that FIDT score, which sums up how well DMM matches each teacher. Figure 4 now gives us a visual way to see that comparison. We're looking at two heat maps here. The left one shows the FID scores for our DMM model comparing its generated styles against each teacher, and the right one is a reference, basically comparing the original teachers against each other. Remember, lower FID scores are better, shown by the darker colors. What you really want to look at is the diagonal in both heat maps. That represents the score for the correct style match. You know, DMM generating style 1 compared to teacher 1, style 2 to teacher 2, and so on. And you can see the diagonal on the left for DMM is pretty dark, and it looks very similar to the diagonal on the right, the reference. This visually confirms what the numbers in Table 1 told us. DMM is capturing those individual styles quite well. So yeah, those heat maps really drive the point home. DMM is doing a great job matching the individual teacher styles. What this DMM paper really shows us is a promising way to merge specialized AI models into one more versatile system, saving on resources while keeping that distinct style quality. It's exciting because it could lead to more efficient and powerful generative AI down the line. Well, that's all for this episode. Thanks for listening to the AI Research Roundup. I'm your host, Alex.